Hi, welcome. Today we're going to talk about nuclear energy. As you may recall, I've mentioned that the nuclei of all elements other than hydrogen were produced by the nuclear fusion processes that take place in stars. Though that process is called nucleosynthesis. All right. And that's just a fancy way of saying making nuclei from simpler materials. When the universe started in the Big Bang, probably the first type of particle that was formed were neutrons, and those neutrons decayed to make up protons, electrons, and some neutrinos and antineutrinos. Other side stories there, but the fact is there were protons and electrons, and those are the makeup of hydrogen. Now when those clouds of hydrogen started colliding and started condensing and becoming denser and denser, they actually became stars, and when the pressure becomes so high, they actually started causing the fusion of those protons to make new elements. Alright, now in the image that we have here, let me just show you, we can see that protons, in the top part you can see the two protons, and let's see if we can circle it over here, two protons, 1 and 2, are coming together to make a deuterium atom. In this particular case, or a deuterium nucleus, it means that the two protons collided together, they fused, the strong nuclear force kept them together, but one of the protons, instead of staying as a proton, became a neutron, threw out a nuclear reaction, emitted a positron, and thus we got this new nucleus that contained one proton and one neutron. Still hydrogen, but a heavier hydrogen. Deuterium is heavy hydrogen. Alright? Now, when that deuterium reacts with another proton, it gives you a new atom. When they get fused together, when they get crushed together, so the strong nuclear force has to keep those nucleons together, we get an atom or a nucleus of helium-3. Helium-3 is a isotope of the more common helium-4 atom. Alright, and that also releases some energy. You can see that in the lower side we have the same process going on. When two helium atoms, helium-3 atoms, are fused together, they are crushed together by the intense pressures and temperatures in the sun, they make an atom of beryllium-6. Now, the atom of beryllium-6 that was formed is unstable, alright, under those conditions, and it actually breaks, it cleaves, it has a fission process in which it releases two protons, and then it gives us an atom of helium-4. This is one of the forms in which we can see the nucleosynthesis of helium-4, and this is a process that could happen in a star like our sun. Alright? Now, nuclear fusion, which you've seen me mention, alright, is a process through which a heavier nucleus is produced by the combination of two or more smaller, lighter nuclei, alright, under conditions of extreme pressure and temperature. Alright, you have to have both of them, so you have a lot of energy pushing those nuclei together, because otherwise the nuclei would want to repel. That's what two positive charges would do. But if you get them close enough with enough pressure, then the strong nuclear force will start acting and will bind them together. Alright? The process of nuclear fusion for smaller atoms is accompanied by a huge release of energy, and is particularly large in the production of helium. That's when we're going to be releasing the most energy, and that's why most stars are converting hydrogen into helium, and that's what our sun is currently doing. Okay, so where does the energy come from? Well, fission reactions will produce energy or will release energy if they make an atom or a nucleus that is lighter than your typical iron nucleus. We're talking about somewhere around a mass number of 56. So an iron 56 is about the heaviest that you can make and actually release energy from fusion. All right, and that energy is actually coming from the fact that some of the mass of the nucleus is actually being converted into pure energy and released in the form of photons, sometimes, most of the time, in the form of gamma rays. All right, so mass is being converted into energy. Here we have just an overview of the fission reaction, of course, the fusion reaction, in which we're bringing two nuclei, all right, and we're going to, with incredible pressure and incredible temperature, we're going to bring them closer together, all right, such so that the strong nuclear force will then take over, overcome the repulsion, and actually bring them together to make one large nucleus. That process also releases energy, all right, because that some of the mass is then becoming pure energy, all right. So the reality is that the sum of all of the nucleons in a nucleus that is lighter than iron 56 is going to be larger. So the sum of the component nucleus is going to be larger, all right, so that's the key part, the greater, than the actual mass of the nucleus, all right. And that mass difference, you know, the mass of the nucleus minus the mass of the components, or it's called sometimes the mass defect, all right, is the mass that mass difference is the mass that becomes energy, all right. And that energy, its official name is called the nuclear binding energy, all right. And it can be calculated using Einstein's equation, E equals mc squared. You may remember that E equals mc squared is equal to energy is equal to mass times the speed of light squared, all right. So in the case of binding energy, how do we write that equation? We write that equation as energy, binding energy, is equal to the change, or delta m, times c squared, which is the speed of light, all right. So if you see, and since we talked about the fact that the nucleus is actually going to be lighter than the mass of the nucleons, it means that the binding energy is going to take a negative value. Negative in terms of energy means that the energy is being released, is being given off, all right. If instead it was a positive value, it would mean that we need to add energy to make this nucleus, all right. And in the case of nuclear fusion, and especially for atoms lighter than iron, that will always release energy, and that's where the solar energy, the sun, gives us energy from the fusion reactions that it's making, all right. So let's go ahead and move on to talk a little bit about a second case, all right. If we have nuclei that are heavier than the nucleus of iron, they will require energy. You will actually have to add energy. You'll need a positive binding energy in order to keep the nucleus together. So that means that the nucleus is actually heavier than its components, all right. It means that energy is added to the nucleus, and that energy is becoming mass, all right, and is helping keep the nucleus together, all right. So if you want to release that extra mass, that extra energy, that energy that was added, you have to break the nucleus and make it into smaller components, and that process is called nuclear fission. So let's look at a diagram of nuclear fission. Here's a little bit of a diagram. If we have, for example, it doesn't necessarily have to happen like this, but it's one of the examples. If you hit a neutron onto a very large atom, that nucleus will split into smaller daughter nuclei and release significant amounts of energy. Sometimes it will release more neutrons, which can then go ahead and break other fissionable atoms or fissionable nuclei. Okay? So the concept of nuclear fission is a process through which a heavy nucleus, normally heavy nucleus we mean a nucleus greater than iron, it's cleaved, it's fissioned, it's broken into two or more lighter daughter nuclei or two or more fragments, and it releases large amounts of energy. All right. The energy in nuclear fission and in nuclear fusion, all right, is the binding energy in both cases. But the big difference is that fusion releases energy when you bring together nuclei to make something that is smaller than iron. Fission, on the other hand, releases energy when you break something much larger than iron into smaller fragments. All right, so that's the process. Fusion releases energy when you make nuclei, but they have to be lighter than iron. Fission releases energy when you break nuclei, but they have to be heavier than iron. Okay? And so we've talked all about that. What about calculating those numbers? So let's see the mass and the important what are the important bits of data that we'll need to have. All right? So in order to calculate binding energy, or the energy released by a fusion or fusion reaction, all right, you need to know the mass of a proton, the mass of the neutron, the mass of the electron, in case you're given an atom. Sometimes you're given the data as atoms as opposed to nuclei. All right, and the mass of the nucleus or the atom that was made. All right, if the mass is given to you in AMUs, you will need to know this conversion factor between AMUs and kilograms, so we can get the numbers in kilograms, because Einstein's equation requires us to use the mass in kilograms. All right, so all of these values you can copy down, you can press pause, you can get them from class later on, but I just want you to see very briefly what those values how we would use them. All right, so if we wanted to calculate the binding energy, all right, stored when we make an atom of helium-4, all right, and we know that helium-4 contains 2 protons, 2 neutrons, and 2 electrons if we're talking about a full atom. All right, and I've looked up the mass of an atom of helium-4 is exactly 4.002602 AMUs, atomic mass units. And so first of all, we need to convert that into kilograms, so we multiply it by our conversion factor, and we get that the number is 6.646477 times 10 to the negative 27 kilograms. Big mouthful there. Now, that's the mass of the entire atom, with its electrons, protons, neutrons, all as it exists. Now, if we were to break it into its component particles, well, we would release the binding energy. All right. If we add the mass of 2 protons, 2 neutrons, and 2 electrons, we get that is 6.696926 times 10 to the negative 27 kilograms. All right. So we see that there is a difference between those two numbers. The mass of the atom, which I've highlighted over here right now, is actually smaller than the mass of its components. All right. So when we were to make a helium atom from its components, energy is going to be released because some of the mass is going to be converted into energy. So we can calculate the mass defect by getting the difference between the mass of the nucleus, or the atom, or nucleus, and this is the mass of the components. And we see that the difference between that is a negative value, and it's negative 5.0449 times 10 to the negative 29 kilograms. A tiny amount of mass. Virtually nothing. All right? And yet, that amount of mass is actually bigger than the mass of the electron. So it is significant. All right? When we put this into Einstein's equation by multiplying it by the speed of light squared, we get that the energy released is 4.54041 times 10 to the negative 12 joules. It's a very small amount of energy, but that's just for making one atom. So just imagine if you could make a mole of atoms, or a even larger amount of atoms, because that's just a mole of atoms is just 4 grams of helium. All right, if you could make a kilogram of helium, you would be releasing hundreds of millions of joules of energy, which is quite impressive. Now, the reality is, this is idealized. This would be the maximum amount of energy that you could release from making helium, because you were making it from its individual components. If we were to make it in a lab, all right, which we can do, but it actually takes more energy because we are not capable of doing this very well. We do it by doing the fusion of a deuterium nucleus and a tritium nucleus. These are 2 isotopes of hydrogen, and when we bring them together, all right, we can see here we've got deuterium on this side and we got tritium on this side, and they make this unstable atom, all right, of helium 5, which will become an atom of helium 4 and shoot out with high energy, will become an alpha particle, and it will also release a neutron. All right, so having illustrated this, we are going to continue working on how to calculate energies through fusion reaction, and next time we'll talk a little bit more about fission. I hope you're taking some good notes. I hope that you will listen to this more than once, stop it, and also download the notes from the website. All right, thank you very much.